So thanks to the organizers for inviting me here, and thanks to everyone for coming to my talk. And so today I'll tell you about exploring some of these questions about probing measurement-induced phase transitions in sort of NIST systems. So that's maybe the connection to NIST. So yeah, let me get started by just thanking my collaborators. So this is a project that got going during my postdoc with David Hughes, and then it extended into this really fun collaboration with Chris Monroe's group, where we were, exploring some of these ideas in experiment. And then recently, what I want to get to at the end of the talk is I think an exciting direction for probing this physics in generic systems, and that's using machine learning tools for the problem. That's a project with Mohammed Hafizi and collaborators. Okay, so I'll just get started off by talking about kind of my perspective on, or the types of systems I've been studying in my throughout my work. So this is what we call monitored quantum systems, and the way I think about it schematically is that we have some many-body quantum system, which is the sort of system of interest, but it's actually an open quantum system. And we're gonna break up its openness into two parts, right? So there's gonna be noise, which is uncontrolled parts of the environment, but then there's also these very controlled aspects of the environment, which include external drives, measurements and mid-circuit measurements, and then ultimately feedback based on those measurement outcomes. And so where the sort of quantum physics comes in this setting is there's an input quantum state, which sort of enters the system, and then there's an output quantum state at the end. But what's interesting about monitored quantum systems is you also have this measurement record, and so we call that, going back to this terminology from quantum optics, we call output quantum states labeled by classical measurement data quantum trajectories. So that's sort of the setting that we're working in. We're going to be studying quantum trajectories in this talk. Okay, so just to give you a sense that this is, really experimental reality and not just a theoretical subject, I want to start off by showing this beautiful experimental data from Michel Devre's group, and Zlatko is actually the next speaker, so I think that, that ties in nicely in the conference. So this is an experiment in superconducting qubits, just two superconducting qubits, which form a three-level system, and then what's going on here is that they're driving it with two coherent fields. They have a dark state, which doesn't emit very often or doesn't decay, and a bright state where you can count every photon from the system. And that's sort of the key aspect of this experiment, is that they're actually doing this measurement of the photon. So if you didn't have this measurement, this would be kind of a boring quantum system, which is just really a three-level matrix. But once you add this measurement data, you get this much richer dynamics, which extends sort of in the time direction. And another really fascinating aspect of this experiment is that they were able to notice these like intermittent switches between bright and dark states and actually use feedback to change the state of the system. So this experiment really illustrates all of the ingredients that we're going to be exploring in this talk. And really the difference is we want to now start thinking about scaling this up, looking at many-body physics in this type of setting. So the other example that I'll just highlight, because it's going to show up later in the talk, is the ion trap. So this is a really groundbreaking experimental system put together by Chris Monroe's team. And so it's a system of ytterbium ions in a one-dimensional chain, but because of the Coulomb interactions, they can actually do gates between arbitrary pairs. So there's no really notion of spatial locality here. And what's really exciting about this experiment is they have this sort of up to 32 ions and 32 beams, so individual control and programmability, and then they also have 32 outputs, so they can individually measure each ion. And this is an example of just what it looks like hooked up in the lab. Okay, so I think, and this ties in nicely to John Preskill's talk at the beginning, I think there's this really nice connection between these monitored quantum systems and machine learning problems, where you think of having a quantum system with measurements, and you can think of asking about learning from quantum systems in that setting. and I'll get into that in the end of my talk. But yeah, I just wanted to highlight some of the work that he presented, telling how these types of problems really raise fascinating questions about the power of data when it's specifically obtained from quantum systems. And then I'm just going to highlight again this very nice example showing quantum advantage in this setting where where it's not a computational advantage, it's an advantage in sampling complexity. So it really gives us new perspectives on how to search for advantage in these types of platforms. So with that, I actually want to move on to, so that's more of a general introduction. Now I want to talk about more specifically what motivated us in these studies. And we were sort of, at least at the beginning, we were more specifically motivated by this idea of fault tolerance. And that's a monitored system and where we're thinking of taking limits of large systems in long time, so going to a many-body scaling limit. And as is well known, these types of systems have phase transition between success and failure at processing of quantum information. So this would be something like an error rate. Above the threshold is the failure phase, and below is the success phase. And I guess what's different about this talk is we're going to define success in a very loose sense. So success is parameters of the system where the output density matrix does contain some quantum information about the input. So the quantum information has been processed by the system. And it doesn't, it may be that it requires exponential classical resources to learn, to recover that quantum information. But there's still some signature of it in the state. So that's a very weak definition of success, much weaker than the conventional setting of fault tolerance. And failure is when the output state, given a measurement record, actually contains no quantum information. So even with access to exponential resources, you wouldn't have information. And the specific question we want to study, and which has this beautiful answer I'll give on the next slide, is what kind of simpler physical models can exhibit phase transitions of this type. And so that leads me to this class of random quantum circuits with measurements. So here we sort of took out the uncontrolled part of the environment, and we're just left with this more. It's still a dissipative system, but it has this simpler structure. So the models which were introduced in these early papers up here show that you have here this is an example of one-dimensional quantum circuit with random unitary gates interspersed with measurements, and you have the input quantum state and output quantum state, and of course you also have the measurement data associated with each measurement in space-time. And then the sort of like exciting observation for us from the perspective we took on the problem, in which Ehud also alluded to in his talk, is that this model has this type of phase transition between successful processing of information below the critical measurement rate and failure above some other measurement rate. And I should also wanted to highlight these two review papers, which are now have come out on the subject, and if you want, there's really a rich variety of behavior in these models, and I think these papers kind of point out some of that. So I encourage you to take a look at them. I think our organizers are some of the authors here. Okay, so let me just say a few words about how this picture works. What's the connection to sort of fault tolerance? And so what we imagine is going on is that you start with some input state, and you have this noisy dynamics of the system. So it's dissipative dynamics, but it's sort of encoding quantum information. But then at some point, the information is sufficiently encoded by this circuit that it actually becomes well protected from the future evolution. So the future evolution on the code space is actually reversible unitary dynamics. And the way this phase transition works is that below the critical measurement rate, there's sort of an extensive number of logical qubits that survive, and then that vanishes at the threshold or at the critical measurement rate. And another interesting aspect of this is that this unitary projective dynamics is not just partially, it's not just encoding information in some weak sense, it actually turns out it's doing it in an optimal way that achieves the channel capacity of the future evolution. And that was explored in these papers. I think, you know, just to highlight some interesting applications of this perspective. So we were able to apply this kind of perspective to get some interesting new results in quantum error correction. There's also been some interesting work using similar ideas, which is maybe much more practical and for fault tolerance, for actually encoding topological quantum error correcting codes with using this idea of a Floquet code. Okay, so that's all I want to say about the sort of general picture for this. So I can actually pause here for questions if there are any. This is sort of familiar material for a lot of the experts.
Just a quick question. When you say success phase, is there any limitation on the depth of the circuit? So I would assume if you have exponential along the circuit, that will probably able to erase information? Yeah,
I guess here we mean that the information survives for exponentially long times in the number of qubits.
Okay, so yeah, so you say, okay.
Yeah, thanks. Okay, so I'll continue. So the next part I want to talk about is moving on to, you know, one specific implementation of these models in this ion trap system. And this is the reference here with the contributors to this work. I mean, this project here was really an example of this co-design type setting where, you know, we have a specific application in mind, and we're trying to really tailor it to the hardware that's available in the lab. And so what we did is we talked to the ion trap people in the ion trap group, and we sort of tried to exploit the natural strengths of that architecture. So one is there's this, you know, beautiful high fidelity Molmer-Sorensen gate, which is the entangling gate, and then you also have all-to-all connectivity. So what that means is that you can get to richer quantum states and lower depth. So that's obviously a pretty powerful feature. And so this is an example of the type of circuit we have in mind. So we're going to start in a state encoded quantum state, and then we'll apply random XX gates followed by measurements. This is a Z measurement. This is effectively an X measurement because these are Hadamard gates. So this is the type of circuit we would study. And I should say there's also a related proposal for ion traps from the group in Waterloo. Okay, so this is the specific model we studied has the phase diagram, so it's not realizing exactly the models that were studied previously, but it has the important physics, which is this sort of coding phase and the failure phase. And the way we set up the model is that there's actually a special measurement basis, so we find it convenient to tune through the phase transition by working at a fixed measurement rate and just changing the direction of the measurement. So I'll be talking about data taken along this kind of vertical axis. This just lets us use fewer measurements in the system. Okay, so now the actual circuits we studied were actually completely unitary circuits with all the measurements at the end. And so the way we do that is we use this idea of deferred measurements. So for every measurement we want to do, we add an ancilla to defer the measurement later. We also use this trick of we actually probe the phase transition using a local reference qubit, and so that makes seeing the signatures of the phase transition easier. And then another really important ingredient in this circuit, which is very special to the fact that we actually choose a stabilizer, Clifford circuits for this model. So this is a way of getting around what Ehud was alluding to, which is this post-selection problem in these models. So we actually add so we can actually add a feedback circuit. So given the measurement outcomes, we can act back on the reference system and put it in a deterministic state depending on the measurement outcomes. And for this circuit, we're able to compute that analytically. So this type of model is fully scalable in that sense. And just a quick comment, you can think of this as a version of this black hole information recovery problem where you sort of threw a qubit into the black hole at the beginning and you try and recover it at the end. I think Ehud was using similar pictures.
So the fact that you can analytically compute it, this is result of some special circuit.
Yeah, when we took the XX gates, we took the angle to be pi over 4, so it's Clifford gate. Yeah, okay. Right, so this is just the data showing the realization of these two phases, this coding phase and the success phase. So here's a simulation of on different system sizes, just to illustrate what we're trying to do. So this is time, and this is the entropy of this reference qubit. And what we want to see is that as you scale up the system size, in one phase the entropy increases, in the other phase it goes down. So that's the basic signature. And you can see that successfully. This is experimental data with theory laid behind it. So the nice thing about this is we have this very good agreement between theory and experiment because we were able to use special error mitigation techniques. But you can see clear evidence of the two phases here. Okay, so we were also interested in actually, it's always, here I was talking about probing the phases. We also want to know, what would it take to see the critical properties in this model? And so we came up with a method that allows you to do that with limited finite size effects. So essentially what you do is you take this decay curves I was showing and you look at the decay rate, you take its derivative essentially, and then you look at the scaling of that quantity. And you can see here that even for modest system sizes up to 32 qubits, we're able to get good estimates of critical properties. So we really think this is, this kind of experiment is feasible in the near term horizon that these ion trap systems are capable of. So there's going to be technical improvements that will be needed. So one, you need longer time evolution, so you have to bring the noise down a little bit. You also have to build in mid-circuit measurements into the system. Essentially, what they do is they sort of split the ions in half and then measure them in a measurement zone. And then they'll have to go to larger system sizes. After our work came out, there was a really nice experiment done on the IBM machine where they were able to probe this 1D criticality actually in a fully random experiment. But in this case, they used like full quantum state tomography. So it has this kind of exponential cost. But it does illustrate the basic physics. Yeah, this is all theory. Yeah, good. Yeah, I'm sorry, I should have been very clear about that. Yeah, no, that would be pretty exciting if we had the experimental data. Yeah, this is all theoretical prediction, but we think it's accessible, in particular because of this error resilience of Clifford circuits, actually. Okay, so now so in the next part of the talk, maybe I should pause for questions on this specific experiment. Yeah.
Could you explain the requirement of the mid-circuit measurements again?
Well, yeah, here we were deferring measurements, and it's, it adds overhead because every measurement you have to add an extra qubit. If you have mid-circuit measurements, I guess what we mean by that is you reuse ancilla, so you don't need as many. Yeah, that wasn't clear. Yeah.
Hang on. Thank you. Could you comment on the fact that the feedback unitary is actually taking place before the measurement outcomes? Like how, yeah.
How do we get?
Exactly.
Yeah, so, right. Yeah, so what's going on here is we're going to use special properties of stabilizer circuits or Clifford circuits. So when this purification, when this goes to a pure state, so it's disentangled from the system, it goes into one specific basis. And then the only thing you have to do is you rotate it to the z direction and you figure out the sign. And so what this circuit does is, for each set of measurement outcomes, there's like a specific sign. And so if it's pointing down, it does like a Boolean logic calculation to flip it back up. And that can be done efficiently. Because it's just linear algebra over Z2, I guess. It's a technical answer, yeah. It's another question.
And so how does the depth of that circuit scales with the number of qubits? The correcting, yeah.
Oh yeah, that we didn't study. It's polynomial, but it's, yeah. Yeah, it's kind of, it's another reason you want to, well, this would be an argument for adding feedback. So it would be nice if you could make the measurements and then do feedback, because then the circuit is, so this involves a bunch of entangling gates. So it's pretty costly. If you have direct feedback, then you would just apply a Pauli operation. Yeah, but yeah, this is a pretty big circuit in some cases. But there's this type of thing is well known in fault tolerance. You can build fault tolerant machines with deferring measurements to the end. It just adds some overhead. So it's okay. Any other questions on the experiment? Okay, so yeah, let me motivate the next part of the talk where we want to look at methods to go beyond stabilizer circuits. And so what I talk about in the experiment are these simulatable circuits, stabilizer circuits. So they're nice because they're experimentally accessible. You really like just tune a parameter in your gate and you have one of these Clifford gates. They're also, because of this feature that things come in just binary integers, they're very robust to noise. So you can sort of threshold things. And then they have this they're decodable analytically, either using direct simulation or there's this nice protocol put forward by Yoshida. But of course, as everyone knows, the gate set is not universal. And in particular, there's a physics motivation to go beyond Clifford circuits, which is it really seems that generic circuits are in a different universality class. So we have this work with Jed Pixley's group and collaborators where we really developed numerical methods on classical computers to really start to distinguish these two critical points. And we have now really convincing evidence that even in 1+1 dimension, Haar and Clifford and percolation are all separate conformal field theories. So there's some physics motivation to really explore the physics of the Haar random circuit where we can't do, it's not obvious how to do efficient simulations. But then of course that leads to this question about decoders. How would we, if we want to do this in a practical setting, we need efficient decoders for the Haar random problem. Okay, so what we're this is kind of exploratory work, taking a machine learning perspective on the problem, but we have some interesting results in this area. And the idea is that we're actually going to solve this decoding problem by treating it as an image classification problem. So if you remember, the way we're probing this phase transition is by adding a reference qubit entangled with the system, and then asking, how does the entanglement survive or not? And that's enough to probe the critical properties of the phase transition. And you can imagine just from locality arguments that as the circuit evolves, like originally only measurements in some region around where the reference qubit was entangled will determine its state. And so there's some natural spatial structure to this problem. And the idea is we want to treat each of these measurement patterns as like an image, which is going to feed back into and then the machine learning algorithm will tell us what's the state of the reference qubit given some particular measurement outcome. So first you train it on, you fix the circuit and you run it many times, and that's your training data, and then you apply it to the system. And so more formally, what it's trying to do is, given a set of measurements, it tries to predict the the expectation value in each of the polybases. And so this is the type of neural network we study. It's a convolutional neural network with like 5 or so layers. And the output is just this sort of binary outcome. So there's a huge compression of information in the problem, which is why it's potentially tractable. Okay, so now let me tell you how we studied this algorithm, at least initially. So, you know, well, before I say that, one point is that one of the reasons we like this approach is that this classifier we're using is only using the measurements as an input. You don't have to tell it the circuit. And so that gives it some intrinsic robustness to coherent noise in the system. So that's a potential advantage. It's not robust to poly noise, but it does have this built-in robustness. So it could be useful on things like quantum simulators, where, you know, like say these cold atom systems. Okay, but then to benchmark its performance on, you know, on using classical simulations, we again turn back to these stabilizer circuits, and the motivation for this is that this sort of image classification process, it's not actually that well suited I mean, Clifford circuit outcomes have a special structure. This image classification doesn't really, it's not really well suited to finding that structure. So we think that its results can be generic. Yeah, question?
What is the problem that the neural network is trying to solve?
Yeah, it's trying to find the state of the reference qubit given measurement outcomes. Find its direction in each of the poly. So if you can determine that, then you have an efficient probe of this phase transition. Yeah. How much? You mean the training data?
How many measurements go into one prediction?
Well, in general, if this was, you know, 200 qubits, it would be the measurement rate times 200 times the number of layers, I guess. Yeah.
As you fix the number of measurements per layer, you have to do that?
No, we generate a circuit and we fix the locations of the measurements. So we have to do this training for each circuit.
How does the machine knows the basis?
It has to, I guess it has to learn this.
Do you need to serve the whole random unitary circuit to the machine?
Yeah, we never feed any information about the gates. We just feed the measurement outcomes in the mid-circuit measurement and then a measurement on the reference qubit.
But how does the machine know which basis it is performing the measurement?
Yeah, so we do 3 experiments, one in each direction. So you're just doing tomography.
Okay.
Okay, yeah. Thanks for the questions. Right. Okay, so then, now we're sort of studying this machine learning algorithm on Clifford circuits. So they have this special property that actually the purification happens in one measurement event. So this is from the experiment actually. So this is in the sort of encoding phase where the reference stays mixed for a long time, and this is in the the failure phase where the reference purifies. And you can also see the effect of noise on this data here. Okay, so what we can do because of this fact, we can take an intermediate step in characterizing the machine learning, which is we can sort of sort the circuits and based on when this purification event happens, at which depth, and that lets us study the hardness of training, or just the number of training circuits required training runs to successfully learn the state, and that's shown here. So in general, it increases roughly exponentially in the purification time, but it's independent of the system size for sufficiently large systems, which is what we're trying to see. And from this feature, so this is the purification dynamics in the 3 phases. So this is just simulation. And so what you can see from this is that such an approach like this will sort of obviously work successfully in the 2 phases, but it will tend to struggle at the critical point, which is this red line where purification events can happen, very deep or at times polynomial in the system size. Okay, so here's an example of the application of the algorithm to learning this entropy dynamics. So this is showing 2 examples in the this is a purifying trajectory and this is a mixed one. So the solid is the learned and the dashed is the simulations, and you can see that they're able to get close to each other. Interestingly, the sort of mixed phase or the encoding phase is actually easier to learn for this setting, and despite the increased quantum complexity of the phase, and that's just because there's actually fewer measurements, so the data set is smaller. Okay, so this I think this is a nice initial result showing that we can learn the 2 phases, which we heard in John's talk. Even at a rigorous level, that tends to be an easier problem. So we also went ahead and tried to see how well we could get critical properties using this approach. And so this is an example of, so we again use this purification dynamics to extract the critical properties. And these we know very well from simulations. So these are the exact or close to the exact values. And then this is to within numerical precision. And then this is what we get from the machine learning algorithm. So you can see you're able to get within 10 to 20% of even of these more detailed critical properties. So this is quite promising, that if someone comes along with a natural system where they can implement a monitored quantum evolution, they can send us, or we can send them the algorithm, or they can send us the data, and we can apply this method to that case. Okay, so there's another interesting aspect of this, which is we also looked at the scalability of the learning, and so here the idea is that we want to see that if you say train the neural network on a small system, does it actually work when you look at a much larger system? So the way we do that is that we actually define these boxes of increasing size, and then we cut out all the gates outside of it and measurements, and then we only feed in that data into the neural network, and then that trains a neural network. We then simulate the full circuit and see if it succeeds on the larger circuit. So do we see if it generalized to this larger circuit? And we indeed see that that's the case. So once the size of this box extends beyond some kind of effective light cone in the system, the learnability saturates to some fixed value. So that's an evidence of that this approach is a scalable learning approach. Okay, any questions on the machine learning aspects? So this is obviously still exploratory work because we haven't implemented it on generic circuits.
So, if I understand, this is not scalable in the usual way that Monte Carlo calculations are scalable, because where you get close to the phase transition, it should become exponentially harder to simulate. So it's sort of like exact diagonalization
you mean whether
it still becomes exponentially hard to go to larger and larger correlation lengths, or am I wrong? So these scalable results you've shown, they're just kind of before hitting that exponential wall, or?
Yeah, as far as oh, you mean like
Yeah, what you showed.
here? Yeah.
Yeah.
Yeah, right. So here
it's
we.
not trivial that you'll be able to learn exponents because you need to do finite size scaling, and
Right.
It's not clear that it's scalable close to the transition.
Yeah. So here here we're doing a finite size study. So we.
64 still already looks quite big. So.
Yeah. So I think it's sort of it's different from classical simulations where you're sometimes limited in qubit number, although not always. But yeah, it's just a different approach to the problem. But yeah, as far as we can tell, this algorithm doesn't, it only goes up to logarithmic depth. So you can sort of estimate the critical point, but you can't get increasing levels of precision. Like your precision of critical properties will be limited.
How can you guarantee that this critical scaling actually works? Because I think in all this phenomena, I think what decoder you choose actually matters, and you can change the critical behavior, observed critical behavior. So for example, learned like parameter here can be actually different from what it is actually, unless you guarantee that your decoder is optimal for this exact point. So
yeah, great.
Is there any nice reasoning for this?
That's a great point. Yeah, we haven't systematically explored that question. So in principle, yeah, and this happens in error correction all the time as another example. Yeah, different decoders have different critical points and critical exponents. And you might worry that by this decoder might be actually yet another critical point. So but we haven't addressed that. That's a valid point. Yeah. I mean, as far as we can tell, we're able to approximate the optimal decoder. Yeah. Thanks for the question. Okay, so with that, I'll end the talk. So just to summarize, so first we looked at this connection between entanglement transitions and these fault-tolerant ideas in fault tolerance. These are some applications to dynamically generated codes, which I think are quite interesting, and we're continuing to follow up on. We also have this reference qubit idea I used throughout the talk. That's what we think of as one way to get efficient probes of this physics. The other work was on this experimental realization in the ion trap system. We have these numerical methods now that can really distinguish these types of systems on classical computers. And then this exploratory work where we're trying to use ideas from machine learning to also get scalable probes in more generic experiments. And then I'll just end with this, this general outlook. So I think, some of the goals of this work is that we would, and this is where we're trying to move with things like this neural network decoder, we would really like to examine more types of systems and include more realistic features like noise and even active error correction in these models. And we're moving pretty actively in that direction. I think another conceptual question is whether this dichotomy between success and failure is really the right picture for this type of dynamics, because there seem to be this rich variety of phases. We should be open to different definitions of success. I think something that ties back into quantum computing is that this question of whether understanding phase transitions and fault tolerance thresholds can actually help you build more scalable quantum computing systems. And in particular, you might wonder if you can actually operate scalable quantum systems, near to phase transitions. That would be one way to reduce overhead. So with that, I'll thank you for your attention.
We have a few minutes for questions.
Hey, I have 1.5-parter. So in the Clifford decoder, did it require knowledge of the initial state? And if not, what happens if you run it on like a non-stabilizer input?
You mean this one?
Yeah.
You mean this initial state?
Like, does the feed forward know about the initial state of the system? The UF?
Yeah, it's assuming you know the circuit.
Is that what you would usually think of for a decoder? That sounds like I mean, I guess you're free to define what you mean, but I would normally think a decoder wouldn't need to know the...
I think I was using decoder in the sense that Ehud was using it, which is more like this black hole recovery problem.
Okay, thanks.
I mean, in general, a decoder is, a map from a big space to a small space. So that's...
Thanks for your talk. So this bit where you're talking about using or training the image classifier analog at small system sizes and then deploying it at larger system sizes. Is one way to think about this literally is like you have a 9-bit picture that you're training on and then something at high resolution that you're deploying on?
Well, yeah, I think it's so one way you could imagine doing this is maybe you initially train your decoder on like classical simulation, but then but then you run it on like a large scale data from a larger scale quantum simulator. That's one setting where this would be natural. Or you could use it to build up like even data from the quantum simulator. You could build it up this way.
Okay. Yep. Thank you.
Any other questions, comments? Okay, well, if not, let's thank Michael once again.